Time is 11 o'clock, so let's begin. The first thing I'd like you to do is just to log on your computer to make sure that indeed the corresponding software was installed on your computer. If you remember last time we began class by restarting your computer. Please make sure that R Studio 10 and R version 2.15.1 is on the computers. Also, if there are other computers by you that you don't remember anybody sitting there on Thursday, last Thursday at those computers and restarting those computers, I would appreciate it if you just, either now or at the end of class, just restart the computer so the updates take place. So for example, like that computer way over there, that computer is going to need to be restarted because I don't think anybody's ever sat there. Okay? So either now or at the end of class, doesn't matter. So does anyone need any more time to check? Everything looks okay? So I would hate for you to take a test and not have the right software on your computers. Do you have a problem? Yeah, if you don't mind after class, just quickly restart. You could just press the off button, hold it down for like a second or two. That'd be the quickest way. Okay. So let's see where we're at here. So today we're going to start chapter 2. Also, project number 1 is due 1 week from today at class time. Did I say project number 1, project number 2? Project 1? I hope I said project number 1. Are there any questions? Okay, so let's start chapter 2. So we're going to talk about inferences in regression analysis. What that basically means is, if I go back to chapter 1, when we first saw this particular diagram here, again, what this diagram is representing is kind of like the whole purpose of what we do in statistics, but put into the context of regression analysis, where what we have is this population, big population of items. It's hard to get at every single item in that population. But we are interested in understanding the relationship between two variables, which we just generically call x and y. And so to understand that relationship, what we do is we take a representative sample outside that population, and we're left with a smaller set of data that's a lot easier to manage. And so again, we're interested in the relationship between x and y in the sample. And the way that we represent this relationship both in the population and in the sample is through a regression model. So we use the sample to estimate what we call the sample regression model. And then we're going to be talking a lot about this inference part of the diagram today. Oops. Let me get my red pen out. So this inference part right here. I want to make inferences from what happens in the sample back to what I think is actually happening in the population. And sure, we know from our regression model that, for example, B1 estimates beta 1. But we would like to make stronger conclusions. We like to say with a certain level of confidence, what is beta 1? And the way that we do that is through using confidence intervals and hypothesis tests. And so that's what we're going to talk about today, is doing confidence intervals and hypothesis tests for the quantities that we would be interested in with respect to regression analysis. So one of the biggest things that we're going to be interested in is this beta 1. It's beta 1 right here. So this is our population model. This is one way to represent it. If I wanted to instead, I could have also represented it like this. We're just working with the expected value of y instead. Note that the beta 0 and beta 1 are parameters, x's are constants, the epsilon has a normal distribution, each epsilon is independent of one another. But we're very interested in this beta 1. Because if this beta 1 is greater than 0, what does that say about the relationship between x and y? As x goes up, y goes up. Okay. If beta 1 is less than 0, as x goes down, y goes down. If beta 1 is equal to 0, what does that say about the relationship between x and y? Basically, there is none, at least in a linear sense. Okay? So we're going to be very, very interested in particular this. Is beta 1 equal to 0 or not? You can think of it this way. If you could actually prove that beta 1 does not equal 0, then you might say, okay, maybe I could use this model that I'm going to estimate, use this model in practice. So I know that there's a relationship. If beta 1 is equal to 0, though, then you might be worried, oh, should I use this model at all? Because basically what I've just shown is that x or y is not dependent upon x. So that's why we're very, very interested in that. And just to help emphasize the point here, suppose beta 0 was equal to 3 and beta 1 was equal to 0. Here's a little plot of, let's say, some sample. I'm sorry, this is, let's say, a population. It's a very small population. Values of x on the x-axis, values of y on the y-axis. And you can see that we just basically have a random scattering of points. And it just so happens in the way that I drew this plot was so that then if I were to actually plot the expected value of y is equal to beta 0 plus beta 1 times x, look what I get, just a horizontal line. So we can see as x is changing, or let's say as x is getting bigger, what's happened to the expected value of y? Not changing at all. Okay, so that's why we want to figure out, is beta 1 equal to 0 or not? Well, how do we make that determination? Well, as you would expect, you use something from your sample. Well, B1 estimates beta 1, so why don't we look at B1? Well, what's the problem with just looking at this? Suppose B1 was estimated B1. Can I conclude that beta 1 is equal to 0? I'm sorry, can I conclude that beta 1 does not equal 0? Just from that? Why not?
It's just an estimate.
Just an estimate. You don't know how good that estimate is. What happens if you went and took another sample, and this time you got B1 equal to negative 0.5? I might be concerned. Or how about if I got another sample and got B1 equal to 0.5? I might be concerned then about the quality of that estimate and what that's telling me about the population itself. So that's why whenever we do hypothesis tests or confidence intervals, in statistics, not just in regression analysis alone, but in the statistical science, we're always very interested in this quantity, the sampling distribution. This is just another name that people often use in statistics to say, what's the probability distribution of a statistic? In this case, B1 is our statistic. Okay? Well, what do I mean by sampling distribution? Well, all of you should have studied sampling distributions before in your very first stat class, but let's just review what this means. Basically it says this: if I were to go out and take a sample, compute B1, go out and take another sample, compute B1, go out and take another sample, compute B1. Suppose I did this a huge amount of times, then what I could do is, let's say, do a histogram of all my B1s that I get, and perhaps that histogram would look something like this. And what this is a graphical representation of what the distribution of all possible B1s that could occur. It represents their distribution. Now, if it just so happens that a value of 0 fell outside of that distribution, then you might be thinking, oh, maybe beta 1 does not equal 0. And that's essentially what we're doing with a hypothesis test. Essentially. Some minor things that I left out, but that's essentially what we're doing. Well, what one can show through using some mathematical, if you've had a mathematical statistics class, you would be able to do this. If you haven't taken a class on mathematical statistics, don't worry about this. I'm not going to require you to do a proof. But what one can show is that B1 itself, its distribution, which I was trying to represent there, is normal. It has a normal distribution. That's why I drew the histogram kind of symmetric. And the mean is beta 1. We actually saw that back in chapter 1. Remember when we talked about expected value B1 is equal to beta 1? We actually went through the proof. And the variance of B1 is equal to sigma squared divided by the sum of all your x's minus the sample mean of the x's squared. That's the sampling distribution. Now that we know how B1 varies, we're going to be able to actually come up with confidence intervals and hypothesis tests so that we can say with 95% confidence, I think the value of beta 1 is between this number and that number. Sampling distributions drive lots and lots of things of what we do in statistics. Okay, some notation. So to represent the variance of B1, I will just simply say bar B1. It's a very common notation. What our book does instead uses sigma squared parentheses B1 and parentheses. I think that's kind of confusing, especially to new students to statistics, because look at, we've already used sigma squared there before. So that's why I don't like to use what the book does for the notation. Well, how can we actually prove some of this stuff? Well, again, you're not responsible for this proof, but I do want to mention it so that you don't think that this stuff is just kind of pulled out of a hat. It's magic, and this is how it occurs, okay? If you're a stat major, you should know how to do what I'm talking about next. You need to make sure you understand that. You'll see it again definitely in Stat 970. Okay, so we've already done this little proof before. Let's talk about how I would prove the variance of B1 was this particular quantity. Well, what I can do is look at, well, what is B1 itself? And again, think of B1 as an actual random variable here. I know the notation that our book uses can be confusing at times in terms of if you're familiar with the mathematical statistics setting, you know that typically we use capital letters to represent random variables. We use lowercase letters to represent observed values of those random variables. Our book doesn't make that differentiation. But whenever you see a quantity such as var B1, you should realize, okay, we're talking about the random variable B1, not the observed value. What will be the variance of an observed value? 0. Okay, thank you. So, B1. So this is a formula I presented, I think maybe the second day in class for B1. I want to take a look at just the numerator here. I want to simplify it, give it a little bit nicer format so I can find this variance that I'm interested in for B1. So what I'm going to do is, first of all, I'm going to multiply this yi times xi and x minus x bar. And then I'm going to take this y bar and also multiply it by that quantity in parentheses. So that's, let's say, step 1. Then step 2, I can move my summation through that minus sign that we see here. So here's my summation. And this one, so that's step 2. Step 3, I can move this y bar outside of the summation. Why? Notice there's no subscript I on it. So what's that summation going to do to it? Well, nothing. So I can move it outside. So there's my y bar. And then look what's left in that part there for step 4. I have the sum of the x's minus the sum of the x bars. In other words, n times x bar. I have n of them. Well, what's n times x bar? The sum of the x's. So look what happens. 0. And so I have this nice little simplification. It makes things a little bit easier to work with for that numerator for B1. So when I want to find in the variance of B1, I use a lot of the properties that you would see, again, in a mathematical statistics class for how to work with variances. In particular, this is actually in the appendix of our book, the variance of the sum of, let's say, some constants A times a random variable Y. Look what happens. I can move that summation through, and also I square the sums. I square the A's. I pull them out of the variance. And this also assumes that the Y's are independent. So applying that idea, remember that the X's are constants, so I can pull that part out. Notice what happens. It's squared there. Then I can push this variance through the sum, and I pull out the constant. I square it. I'm left with just the variance of y sub I. And we saw, I think it was last time, that the variance is simply sigma squared. Then this part here cancels out with the squared term. And here's my variance. There you go. That's all there is to it. But again, it's helpful if you have a more mathematical statistics class in order to do this kind of a proof. Also I want to point out is that since I can represent this B1 as a simple function of y sub I, that's why I have the normality. Because remember, y has a normal distribution as well. Okay. Well, now there's one little problem with this variance that we got here. Could I ever actually calculate it in practice? Could I actually calculate this? No, because sigma squared is going to be unknown. It's a parameter in the population. So what do? Well, what you typically do in statistics is you have something unknown. Let's just replace it with its estimate. And so we learned about last time that we can estimate sigma squared with the mean square error, or MSE. Simply, just as a reminder, MSE is the sum of the yi's minus y hat squared over n minus 2. So now my estimate then of the variance of B1, notice how I have a hat on top of var. So this is a different quantity than what we just looked at up here. My estimate is MSE divided by the sum of the x's minus x bar squared. Again, our book uses this notation here that I won't use because I think it's kind of confusing. Well, where do we use this estimated variance? Why were we looking at it? Well, again, big picture is that we want to do a hypothesis test for beta 1. And this variance allows us to determine how does possible values of B1 vary. So that will help you make a judgment of, well, if I get a B1 of 3, is that far enough from 0 to conclude that indeed beta 1 does not equal 0? So, in your first stat course, you looked at a hypothesis test such as this for the population mean. Let's say mu 0 is just some number. I'm testing, is mu equal to maybe 3 versus mu does not equal 3? What was the test statistic that you would use for that? Or what was the very first test statistic you would use, that you learned to use for that? A z. How about we call it z star? Z star is equal to what? X bar, where let's say the x's are our data, minus mu 0, or mu, divided by the square root of the variance of x bar. And what was that variance? Sigma squared divided by n. Hopefully that looks familiar. Now there was a problem with doing this. What was the problem? What's sigma squared? Again, a population quantity. So instead what you actually end up using in practice always is T star, let's say. And it's essentially the same thing, except for in this denominator you have the estimated variance of x bar instead. And what was that estimated variance? S squared divided by n, where S squared represents the usual old sample variance. Okay. Well, what we like to be able to do is form the same kind of version of a test statistic here. So what we end up doing is you can look at B1 minus beta 1 divided by the square root of the variance of B1. But again, that variance of B1 contains sigma squared, so we can't actually use it. And instead, we use this as our test statistic. B1 minus beta 1 divided by the square root of the estimated variance of B1. That's going to be our test statistic for doing a hypothesis test about beta 1. Now, what one can show then is that if you think of T star as a random variable now, T star has a T distribution. Well, remember in your very first stat course, you learned about how this had a T distribution with what degrees of freedom? N minus 1, right? Now, this particular statistic is going to have a T distribution as well with now degrees of freedom N minus 2. We lose the 2 there, or we have the 2 there because we're estimating beta 0 and beta 1. So, now that we have a test statistic and its corresponding distribution, that distribution essentially is what is helping us determine the variability of possible values of B1. In other words, it's essentially playing the role of a sampling distribution, taking into account the variance. So now we can formally state now a hypothesis test. We will typically always be interested in the hypothesis test for beta 1 is equal to 0 versus not equal to 0. I'll talk about other hypothesis tests involving beta 1 shortly. And here are 5 steps that I would like you to follow whenever you do hypothesis tests. Ideally, I'd like you to number them so that I can find the stuff and, when you're writing everything out. And I typically, like on a test, will assign, let's say, maybe 1 point per part, or per step, I should say, for a hypothesis test. So, step 1, state HO and HA. Beta 1 is equal to 0 versus beta 1 does not equal 0. Remember again what beta 1 equals 0 means and what beta 1 does not equal 0 means. No linear relationship versus a linear relationship. State your test statistic. In this particular case, since I'm testing beta 1 is equal to 0 versus not equal to 0, what happens to this guy right here? It becomes what? Perhaps that question is too easy. It becomes 0. Okay. Now remember, again in your first stat course you should have learned this, we always assume the null hypothesis is true when we do a hypothesis test, and we look for evidence to disprove that assumption. Well, by saying beta 1 is equal to 0 in that test statistic, you are essentially saying, let's assume that beta 1 is equal to 0, the null hypothesis is true, and we're going to look for evidence against it. This T star has a T distribution, so what do you think we're going to use for a critical value? Quantile from a T distribution. Note that I can either be greater than or less than to reject. In terms of beta 1 is greater than 0 or beta 1 does not equal 0. So that means that this is a, what kind of test? What do we often refer to it as? Two-tailed test. Some people might call it a two-sided test. So that's why we have both a plus and a minus critical value. So we have 2 critical values, just like what you did for a hypothesis test for mu equals 0 versus, for mu equal to mu 0 versus mu does not equal mu 0. And our critical value is the 1 minus alpha divided by 2 quantile from a T distribution with n minus 2 degrees of freedom. So, for example, just to make sure you understand what I mean by a 1 minus alpha divided by 2 quantile, how about I just simply draw out a T distribution. So I'm going to use the curve function that we've looked at before. I'm going to say curve EXPR equal dt, which stands for distribution, T, x equal x, degrees of freedom. Oh, let's go with, let's just say 18 degrees of freedom. I'm going to plot this t distribution from, oh, let's say -4 to +4 on the x-axis. So there's my t distribution. And if I want to find a quantile for this t distribution, I can use the qt function, which we actually looked at in our introduction to R last week. I can say qt probability equal, suppose alpha is 0.05. So I have 0.975. 1 minus 0.05 divided by 2 is 0.975. Degrees of freedom of 18. So there's my quantile, 2.1. And again, I'm going to have a positive and negative version of it. Just to show you on the plot where that would end up, I'm going to use a function that we saw also last time called AB line. I'm going to use it in a different way than we did before. I can draw vertical lines with the AB line function using the V argument. I'm going to draw a vertical line at that critical, that quantile. Well, let's make it a color equal red so it stands out, I should say. And there's one critical value. And if I were to look at the negative version of that critical value, there we go. Or I should call it critical value. I talked about that. Oh yeah, I guess I have, yes. So those are my two critical values drawn to scale. Step 4 then of the hypothesis test, we decide if we reject or don't reject HO. So here's a version of that plot that I just kind of showed you, but now I've also labeled the rejection regions and the don't rejection regions. Again, these ideas should look very familiar to you in terms of a hypothesis test for a mean. So for example, if my test statistic, let's say T star, fell right here, what that's basically saying is that this would not be unusual to have a value of T star there, because it's in my don't reject HO region. If instead my T star, let's say, fell out here, that's in my rejection region, and that would be unusual to have something out there. Well, why is it unusual? Take a look at the probability distribution. Look at the area underneath the curve. Area underneath the curve corresponds to probabilities. So I have a lot of probability underneath the curve here. That's why it's not unusual. I have very little probability there, so that's why it is unusual. Conclusion. Well, if you end up rejecting HO, X is linearly related to Y. You have proven it. This is how you prove stuff scientifically, that you have a relationship. Note that I have X and Y underlined there. That's just to emphasize that you should phrase this in the context of the problem. So if X was high school GPA, Y was college GPA, just replace the X and Y with that. Don't reject HO. There's not sufficient evidence to show that X is linearly related to Y. Why didn't I say X is not linearly related to Y? Why didn't I say that beta 1 is equal to 0 if I don't reject HO? Now let's go up here. If you don't reject HO for this particular hypothesis test, would you ever say mu is equal to mu 0? I hope your instructor didn't tell you that you could say that in your first SAT course. Why? Why can't you say mu is equal to mu 0?
They've assumed it to be true. You just show there's no evidence it's not true.
Essentially, yes. Yeah. We just assumed that HO was true. The key thing with hypothesis testing, that's one reason why some people don't like it, is that you can never prove your null hypothesis to be true. If you need a review on that, contact me after class. I can show you some of my study notes that demonstrate that. Okay. So we can never conclude that HO is actually true. So that's why I say, well, basically what I'm saying with that don't reject HO there, that statement, is that it could be true, or then again it might not be. And maybe it's just I don't have a large enough sample size to actually prove that beta 1 does not equal 0. That could be a reason. So that's how you would do the test using a test statistic. You could also do the test with a p-value. And just as you learn in your first stat course, of course, you're going to get the same answer. But sometimes p-values are more convenient to work with. So step 1, using a p-value, state your hypotheses. Step 2, state your p-value. Calculating the p-value here again as you would for a test for mu is equal to mu 0 versus not equal to mu 0. And that is 2 times the probability, random variable t, with a t distribution with n minus 2 degrees of freedom, is greater than the absolute value of the critical value. In other words, again, just as a review for p-values and hypothesis testing, with a test statistic, we are simply looking at where do values lie on this x-axis. Now with p-values, we're looking at areas underneath the curve. And so now I'm looking at this area right here. If that area is small, reject HO, meaning it's unlikely to have a T star that big in absolute value, if HO is true. If that area is big, then it says, well, it seems like it's a reasonable thing to have happen to have this value of a T star, if HO was true. The reason why we have a 2 there is because, again, we're doing a two-tailed test, or two-sided test. Step 3, state alpha. Step 4, of course, p-value. If it's less than alpha, reject HO. If it's greater than alpha, don't reject HO. Step 5, state your conclusions, seen this before. Okay. So how can we find then these p-values and critical values in R? Well, I showed you how to find a critical value using the QT function. P-values, guess what? There is a function called PT for probability T distribution. So for example, let's just say that I wanted to start off with this. I want to find the probability that a random variable T with n minus 2 degrees of freedom is less than 1.96. For some reason I wanted to find that probability. Then in R, I use the PT function. Q for quantile, 1.96. DF for degrees of freedom, 10. This gives you the area to the left of 1.96. So if I go back to this plot that I drew earlier, we can see where 1.96 would fall, where my mouse is right now. You can see that there's a big area underneath the curve to the left of it. Well, that's why that probability was so big. But our p-value that we're going to end up going to calculate, remember, is 2 times the probability that now we are greater than some observed number. So how do I find that? Well, the 2 parts, fairly simple. To do the greater than part, now instead of just taking just the PT function itself, now I take 1 minus the PT function instead. So in other words, what I end up calculating is this, 2 times 1 minus the probability T random variable is less than the absolute value of the test statistic. ABS allows you to do absolute value in R, and I get a value of 0.078 for that particular p-value calculated in that manner. Any questions? Okay. Well, what about a confidence interval? Maybe sometimes you want a confidence interval instead of doing a hypothesis test. So, again, in your first stat course, if you were to find a confidence interval for mu, and we actually did this last week, you would do something like this. X bar plus or minus the value from your T distribution, 1 minus alpha divided by 2 quantile, degrees of freedom of n minus 1 times the square root of the variance of X bar, and then a hat over the bar. This variance ends up being S squared divided by n. Okay, that should look familiar. We are essentially going to do the same thing here. Instead of X bar, now we have B1. So, notice how this formula then for the confidence intervals looks basically the same. So again, B1 replaces X bar, and instead of having n minus 1, we have n minus 2. I guess just for emphasis, depending upon if you saw this again in your first stat class or not, notice how I write this in a very compact form, B1 plus or minus a quantity. You can equivalently rewrite it like this, where you put the use the negative part here, and then use the positive part right there. That just helps emphasize more. It's an interval for beta 1 itself. So that's the confidence interval. Let's do some calculations here.
Question?
Yeah.
Is the estimate bar should be divided by n, right?
No. No. Again, look what you're doing here. The variance of x bar, and it happens to be s squared divided by n. Okay? And essentially, the sample size gets factored in via right here. Okay? So, this is that sales and advertising, very simple example that we looked at previously. Is advertising linearly related to sales? I mean, in actual application, you want to know, well, is it really worthwhile for me to actually use this model that I just computed, that I estimated back in Chapter 1? Is it worthwhile? So, it's worthwhile, at least to some respect, if beta 1 does not equal 0. So let's do a hypothesis test for that. So I state my hypotheses. Step 2, I give my test statistic. Previously, we calculated B1 to be 0.7. I subtract off 0 from that, so I just get 0.7 back. And this estimated variance of B1, how do I calculate that? We computed MSE last time. It was 0.3667. Then I just simply need to take the sum of the x minus x bar squared. So I have a nice little table there demonstrating that the sum is actually ends up being 10. Plug that in there, and I get 0.1915 for my square root of my estimated variance of B1. So that my test statistic ends up being 3.65. Here are my critical values. If I think I forgot to mention alpha is 0.05. So I can go to R, use the QT function, and I get 3.18 for my critical value. And then also take a negative of that as well. Then I plot everything out. This again helps me see, well, what's a reasonable value of T star if the null hypothesis is true or not. So I plot everything out, my T distribution. Here are my two critical values. And here's my test statistic, T star. Notice how it's far out on the edge of that T distribution. What that's saying to you is that it's not very reasonable to have beta 1 equal to 0, because there's very little probability that far out underneath that part of the distribution. So, and I actually say, and I expect you to do something like this, since 3.6 is greater than 3.182, reject HO. So, advertising is linearly related to sales. Great. Any questions? Let's look at the high school and college GPA example. Let's say I want to use alpha 0.01, just to be different for this particular problem. As we have seen before, I can use the LM function to estimate my model. I can use the summary function to summarize the results from LM. The key parts of the output for this hypothesis are pointed out there. First of all, here's B1. Then we have this column called STD period, space error. It stands for standard error. Again, the word standard error in statistics is just another way to say the square root of the estimated variance of a statistic. Or you can say It's the standard deviation of a statistic. That's just what standard error means. It's 0.073. My t star values represented in the t value column, 9.559. So this comes about through taking 0.69966 minus 0 divided by 0.07319. P-value, 1.78 times 10 to the negative 8th power. Okay, so let's do the steps. Step 1, state HO and HA. Beta 1 equals 0 versus beta 1 does not equal 0. Step 2, how about we use the p-value? It's given to us. It's going to make things easier for us, so let's go ahead and use that. 1.78 times 10 to the negative 8th power. State your alpha. Then compare the p-value to alpha. P-value is less than alpha, so reject HO. Thus, high school GPA is linearly related to college GPA. And there you go. That's all there is to it. So on a test, if you had to do a hypothesis test like this, would you typically use a test statistic or a p-value to do the test? Remember, you got a computer in front of you. P-value, because it's going to save you one step, because now you don't have to worry about finding the critical value on in R. So, when you're pressed for time, again, think of the easiest way to go about doing stuff. Don't do it the hardest way. Use the p-value method. Okay, I just want to briefly talk about this p-value some more. I know from teaching an introductory stat course many, many, many times, I know that it can be somewhat hard to fully understand what a p-value represents from your first stat course. So what this p-value, this small of a p-value is basically saying to us is that if HO is really true, beta 1 is equal to 0, then having a test statistic this large in absolute value should only occur about 2 times out of 10 million. If HO was truly beta 1, if HO was truly correct. So you can see what this is saying is that HO is very, very, very unlikely to be correct. So why don't we conclude HO is false and conclude HA is true. That's how we do hypothesis testing. That's what a p-value is representing here. Of course, whenever you do a hypothesis test, you should try to always think about, well, does it make sense in terms of this data for me to reject HO? So what you can do is go back to your scatter plot that you saw. Look at that regression line. Look at where the points are. Well, yeah, it does make sense that we rejected HO. It looks like there is a relationship there. Okay, good. Now, just to give you one example, what happens when you don't reject HO, because in real-life applications, that's going to happen sometimes. I'm going to give you not a real-life application, and that is, suppose we wanted to look at the relationship between pizza consumption by freshmen on campus and also their college GPA. Is there a relationship? As you eat more pizza, does that mean your GPA goes down? I don't know. I made this data up. Again, you should never make data up, except for if you're teaching a class. Okay. So what I have here, we're going to look at pizza consumption as my X, and Y is the GPA. So the same college GPAs as we had before. And so I simply read in the data using the read.table function. You can look through the details on your own there. I estimate the model using the LM function. So here's my response variable. Here's my predictor variable. I summarize the results from estimating the model so that my estimated model ends up being this. College GPA, I'm going to put a hat on top of that to emphasize that now this is an estimated quantity, is equal to 2.47 plus 0.0075 times pizza consumption. Here's B0. Here's B1. Here's my square root of the estimated variance of B1. Here's T star, and here's my p-value. Also, here's a plot of the data with the sample regression model plotted on it. Notice the plot of the data looks like a fairly random scattering of points. The line that's on that plot is pretty horizontal. So when you see something like that, you should kind of expect, yeah, I'm probably not going to be able to reject HO here. And indeed, you go through all the steps. Again, here's my p-value. It's greater than alpha, so don't reject HO. What this means is that there's not sufficient evidence to show that the number of times students ate pizza during their freshman year is linearly related to college GPA. That's all there is to it. Any questions about that? There's something else I want to point out here. Remember where we find MSE in the output? Actually, it's square root of MSE. It's 0.7317 for this particular data set, the pizza data set, you could say. Let's find square root of MSE from using high school GPA. Right there. 0.297. So it's a lot lower than with using pizza as my X. So what does that say then? What does that mean for us? Especially if we wanted to, let's say, use either high school GPA or pizza consumption to predict Y. What does that mean?
The standard of the high school GPA is a better predictor of college GPA.
Yeah, high school GPA is a better predictor of college GPA. Again, look at the formula for MSE. Remember how it's the sum of yi minus y hat I squared divided by n minus 2. Remember that n is exactly the same for both examples, 20. So what this is saying is that the sum of the squared errors is much lower when I use high school GPA. In other words, those points are much closer to that line, if I were to plot it, that regression line, when I use high school GPA than if I use pizza. Later on in the semester, I think chapter 9, we're going to use this MSE and other quantities as well as a way to determine, well, which variable should I use in a model? You know, right now we're just concerned about, let's say, just one variable right now, but you can have more than one variable in your model. Our book starts with one variable right now just to set the stage for more complicated models later. But you can think of then using this MSE as a way to choose variables to include in your model. You want a model that has the smallest MSE possible. The smaller the MSE, the better the model is going to do a prediction. Okay. Now, one could do other kinds of hypothesis tests for beta 1. For example, you could test, is there a positive slope? Meaning in HA, put that positive slope in there, and then in HO, of course, would be the opposite, less than or equal to 0. Alternatively, you could test, is there a negative slope as well? From your first SAT class, once again, you often refer to these as one-tailed tests or one-sided tests. In particular, somebody might call this a right-tailed test. Somebody might call this particular one a left-tailed test. In this particular case, then, since you only are looking at one side of that distribution, you only have one critical value. So on a right-tailed test, look what you're doing. Your inequality sign is pointing to the right. And you're looking to see, is T star greater than that quantile from the T distribution? One quantile. And notice you only have 1 minus alpha there versus 1 minus alpha divided by 2. Similarly, for testing it for a negative slope, you have a critical value that's on the left-hand side of the distribution. And you're looking at is T star less than that critical value. Now, instead of only testing, for 0, meaning greater than, less than, or equal, or not equal, you could have beta 1, let's say, equal to 1 or 2, some number other than 0. You could do that. Here's one particular instance where this is important. If you're interested in finance, or if you've ever, let's say, simply look at, there's a variety of different financial websites out there. And for each stock, if you look at a financial website, look up one particular stock. What you'll typically see there is a number of statistics listed there corresponding to the stock. One particular statistic that's usually listed is what's called a beta coefficient. And all that beta coefficient is, or that's what's called beta coefficient, all that is B1 in a regression model. That's it. Specifically, they use, for your predictor variable, they use the daily return for, let's say, the stock of interest. So maybe if I'm interested in Berkshire Hathaway, for example, and what I could do is observe, let's say, at the beginning of trading today, let's say Berkshire was trading at $84 per share, Class B shares of the stock. And let's say then at the end of the day it was trading at $85 per share. What that would mean is that my return for that particular day would be 85 minus 84 divided by 84. In other words, I made a 1.1% or 1.2% profit, essentially. My stock has gone up 1.2%. And so that's your X. So you can imagine, let's say, collecting this data over a number of months, maybe. Observing this daily return. Also, your Y is the daily return for the average stock. And what that typically means is some index that's used instead. So maybe you look at the S&P 500 index, look at how that has changed per day, and use it as your Y. And then estimate a regression model using this X, using this Y. So, in that particular case, one is very interested in beta 1, the slope. Obviously, you're estimating it with B1. And if beta 1 was greater than 1, what do you think that means for your stock of interest? So remember, beta 1's a slope. So what does it mean for a slope to be 1 or greater than 1? Remember, X and Y are essentially being measured on exactly the same scale. So if beta 1 was greater than 1, what does that mean in terms of investing? Kind of. What it's actually, I think this is what you're getting at, as let's say as the average stock is going up, Berkshire Hathaway is going up faster. But what that also means is as the average stock is going down, it means Berkshire Hathaway is going down faster as well. So you have to look at it from both perspectives. So you could draw, let's say, a little plot here. Here's X, here's Y. Here's a, just to make this easy, suppose, let's just say that beta 0 is equal to 0, just to make this easy. There's a 45-degree line drawn out from the origin. Okay, this would be then beta 1 is equal to 1. Try it on your own to show that indeed that is a 45-degree line. And if instead my line was up here, that shows you that that the stock is going up faster than the average stock, and it's going down faster than the average stock. Excuse me. Then you might be interested in, well, is beta 1 less than 1 as well? So in terms of investing then, you're interested in doing these kinds of hypothesis tests. And how do you do it? Well, simply similar to what we've done before. Now instead of putting a 0 in there for beta 1, put like 1 instead. That's it. I guess one last thing then. Typically then what you will see on these financial websites that if they will give you the actual value of B1 itself. They won't actually do hypothesis tests. At least what they're presenting on a simple financial website. And basically, if B1 itself is greater than 1, then they will say that this stock is riskier than an average stock. If B1 is less than 1, it's less risky. So, for example, typically you think of utilities as a less riskier kind of investment. Well, typically B1 for those utilities will be less than 1. A stock like, let's say, Facebook probably has a B1. I haven't looked at this. Probably has a B1 that's greater than 1. There, homework assignment. Go look. See what B1 is for Facebook. Okay, any questions? Now, you could also do a hypothesis test for beta 0, but typically this is not going to be very meaningful for most problems. Here's the reason why. Suppose you observe data for your x's from 10 to 50. Would it make sense to do a hypothesis test for, let's say, beta 0? No. Why? Because remember what beta 0 is representing. At x equals 0, this is where your regression model, let's say, is hitting that y-axis. So that's why typically we do not do hypothesis tests involving beta 0 itself. However, there are times where you can. We'll look at one time, I think in chapter 4, perhaps. And one could still go about doing the hypothesis test in much the same way as we did with beta 1. I'm not going to go over the details here. You're not responsible for details. I won't ask you a question on the test regarding beta 0, at least for this particular test coming up. But it all comes down to getting the sampling distribution for B0. That then leads then to a distribution, a t distribution for t star, and go from there. Page 18. So, this is just a very small section. It talks about, remember, although we didn't go through all the derivation details, everything comes down to, in terms of derivations, this right here. The epsilon is distributed independent normal 0 sigma squared. Again, in a Stat 970 class, you would go through the derivation details. You'd be responsible for those kinds of derivation details. But what happens if this assumption doesn't hold? Suppose it's not normal. Suppose it's some other distribution that you know or don't know. Well, fortunately, in a very large number of settings, these sampling distributions that we end up getting for B1, for then eventually T star, still are good approximations, meaning B1 is approximated well by a normal distribution. T star is approximated well by a T distribution. So in the end, there's not much that one needs to be concerned about. Okay, page 219. So far today we've been focused on looking at this beta 1 right here. But there are other times when you might be interested in doing inferences about the expected value of y. So for example, related to the high school and college GPA example, let's say that you work at the college admissions office and you have this regression model that you're using to determine who gets admitted and who doesn't. And let's say some student with a high school GPA of 2.5 applies to the university. You get a y hat out of maybe 2.7, or let's say 2.3. And you need to decide, should we admit this person or not? Well, what's the problem with only using y hat itself to judge how that person is going to do? Do you think that person is going to have a GPA of exactly 2.3? You have to account for the variability out there. And also, you have no measure of accuracy as well. So instead, what we would like to be able to do is come up with a confidence interval. Maybe something like this. And if you have to if in order to graduate, you have to have at least a 2.5. We'll do that. In order to graduate, let's say that you have to have at least a 2.5 GPA. And if you see a confidence interval like that where you're 95% confident, you might say, okay, well, let's give the student a chance. So 95% confident that based upon my model, that their true GPA is going to be somewhere between 2.1 and 2.6. Okay. Well, there are other instances, though. Instead of just looking at y itself, you may be interested in expected value of y. So now you want to know, for students, notice how I use a plural, for students with a high school GPA of, let's say, 2.5, on average, how are students going to do here at this university? So you can come up with a 95% confidence interval as well for the expected value of y. And that might be useful as well. So that's what we're going to talk about. How we can come up with a confidence interval for the expected value of y. First of all, some notation. This is the book's notation. I just decided to keep it. To help differentiate this y, this expected value of y, this x that we have from things that are in our sample. Our book always puts a little subscript h there. That's all. It's just to help differentiate stuff that appears in our sample. So what I want to know is, on average, what is y at a particular x called x of h? Well, the estimated value of the expected value of y comes about through just simply using the regression model, the sample regression model. So b0 plus b1 times x of h leads you to y hat sub h. And then, again, we're going to need a sampling distribution for this y hat, because we like to know how is it going to vary. So what one can show, and again, don't worry about this. I'm not going to ask you to prove this. One can show that y hat has a normal distribution, and look at its mean, expected value of y, in other words, beta 0 plus beta 1 times x of h. And there's your variance. So sigma squared times quantity 1 over n plus x of h minus x bar squared divided by that sum of the x's minus x bar squared. So that's the sampling distribution. Using the sampling distribution, one could go through some derivations and eventually find this. That y hat minus expected value of y divided by square root of the estimated variance of y hat has a t distribution with n minus 2 degrees of freedom. Well, what's the estimated variance here? Where you saw the sigma squared before, the MSE. So now I have this t-like quantity. You can imagine then, based upon what we just got done doing before, how I can now do hypothesis tests, how I can do confidence intervals involving this particular quantity. Typically, we don't do hypothesis tests for the expected value y. We just typically just focus on a confidence interval instead. So here's the confidence interval. Again, compare this to what we had before. You have the estimator, y hat, plus or minus the value from the t distribution times the square root of that estimated variance of the estimator. There's something interesting to look at, too, in this variance, and then the confidence interval itself. Look at the effect of the distance that x of h is from x bar. So to put it into an example context, the high school GPA example, let's say the mean GPA was 3. And let's say the x of h that I'm interested in is maybe 4. compare that to if x of h was instead 3.1. What's going to happen to this variance here? What's going to happen as this distance between x of h and x bar increases? What's going to happen to the estimated variance? It's going to go up. Okay. How does that affect my confidence interval? It's going to make the confidence interval wider. Exactly. So, the closer you are to x bar, the narrower in width your confidence interval will be. The farther that you are from x bar in terms of the x of h, the wider the confidence interval will be. Now let's think about why that might make some intuitive sense then. When you're around x bar, you're kind of in the center of your data, you could say. So you have a lot of information right there. Well, that information then is represented by a narrower interval, or in other words, a smaller variance. But when you are farther from the center of your information, if you're way on the outskirts of all the information you have, you might be a little bit more worried about, what information you have way out there. And so to represent that information then, we're going to make the variance larger. And look what happens to the confidence interval. It becomes wider. Okay. So, as I said before, this particular quantity has a t-distribution. Well, how does that help us then to get a confidence interval? Now, hopefully, again, in your first stat course, your instructor actually went through the details of how a confidence interval for mu comes about and did something just like what I'm going to do here. So, if they did not do that, well, shame on them. And now we're going to go through it in the context of this confidence interval with expected value of y. If your instructor did do it, this is going to be review. So, I know that this y hat minus expected value of y divided by square root of the estimated variance of y hat has a t-distribution. I want to use that to help me find a confidence interval for the expected value of y. The way that I do that is to basically use, what does having a probability distribution mean? Well, it means that I can find two different quantities from that distribution, in this case a t-distribution, and I know what the probability is of being between these two quantities, 1 minus alpha. So for example, we're into numerical context. Let's say that alpha was 0.05. Let's say I have 18 degrees of freedom. I get 2.1. So what that would mean then is that I would have a negative 2.1 here and a positive 2.1 there using the symmetry of a t-distribution. And the probability that this quantity in the middle between these two numbers is 0.95. Now, remember the ultimate goal, though, is to find a confidence interval for this guy. So in other words, I just want to do some algebra so the expected value of y is right in the middle and nothing else is right next to it. So let's do some algebra. Let me blow this up a little bit to make it easier to read. So this is step 1, let's say. Step 2, I'm going to take this square root, the estimated variance. I'm going to basically multiply the 3 parts of that equation inside that probability by that square root. Then, in step 3, I'm going to take this y hat sub h, and I'm going to subtract that y hat from all 3 parts. And here's the end result. So I'm almost there. I have a negative expected value of y in the middle. So step 4, what I'm going to do is multiply through by negative 1. And of course, when I do that, that negative disappears there, but I get a negative there. Look what happens to the inequality. Whenever you're multiplying through by negative numbers, you're working with inequalities. The inequalities change directions. Get that. No longer have a negative there, and I have a negative there now. Well, step 5 then. Let's now get the inequalities going the right direction. Typically we always want to have the smaller number first, the larger number last. So I'm going to move this, put it here, move that, and put it here. Please note that little error in the notes at the very last step. Last, what I do for step 6, again I use the symmetry of the t-distribution. And I replace that alpha divided by 2 quantile with the 1 minus alpha divided by 2 quantile. And take into account the symmetry so that now I have a positive number instead of a negative number there. So what you have here now inside this probability statement is the confidence interval. Again, you would have went through the exact same steps when you did a confidence interval for mu, your first stat course. Just would have had different symbols in there instead. So, when I compute this confidence interval, then I put the observed values from my statistics in there for the random variable statistics. So that y hat then becomes an actual observed value, for example. Does that confidence interval have a probability of 1 minus alpha of having the expected value of y in it? No, it does not. Why? Do any confidence intervals have, so suppose I calculate a confidence interval for expected value of y. Suppose it's 3. It's less than expected value of y, it's less than 3.5. Suppose that this is a 95% confidence interval. Does this interval have a probability of 95% of being correct? No. Why not? Yeah, it either contains it or it doesn't. Okay? But I just said up here, I have a probability. What's the difference? Go ahead.
It's the theoretical or the, you haven't plugged in the numbers and you haven't taken a sample. That's for all possible samples.
Exactly. And this is where the notation with our book can get confusing. This probability statement is using random variables. Random variables have probability distributions. If you have probability distributions, you can find probabilities. But when you actually compute the observed value of a statistic, is that a random variable anymore? No, it's an observed value, and you're able to come up with stuff like this, 3 to 3.5. But now you no longer know what's the probability that this is correct. Instead, what we typically do is we interpret confidence intervals such as this in the following manner. That all intervals that are computed in the same process like this, 95% of them should in fact contain the expected value of y. The probability of one particular interval, though, you don't know what that is. Okay. I have some blank stares when it comes to this little part there. I strongly recommend that you review your notes from your very first stat course if that is what I just said is not familiar, and ask questions if you do have it, because it's a fundamental concept of statistics, is to understand the difference between saying an interval has a 95% probability versus a 95% confidence level. Okay, are there any questions? And that's it for today. Again, if you see any computers around you that maybe were not restarted last time, please restart those computers before you leave.